Good morning. Today we'll discuss about Bohr's atomic model. So there are certain postulates given by the Bohr. The first one is the atom, which is made up of mainly two parts. One is the central nucleus, and around which negatively charged electrons are revolving. That is the second part. So at the nucleus, where nucleons are present, nucleons are nothing but proton and neutron, and the protons are positively charged particles and neutrons are neutral particles. Okay, and the maximum mass of the atom is concentrated at the nucleus. Okay, the second postulate is the negatively charged electrons are revolving at a definite distance from the nucleus in a circular path, and they are said to be orbits. And they are denoted by, say, n is equal to 1, 2, 3, 4, so on, or k, l, m, n, and so on, respectively. Okay, and the third point is, say, these orbits are said to be a stationary states because the energy of the orbit or the energy of the electron will not change. They are fixed. Hence, they are said to be stationary orbits or stationary levels or states, and energy of the electron remains same or the constant in that orbit. That means each orbit is associated with a definite amount of energy. And orbit is nothing but it is the path of revolving electron. Orbit is nothing but it is the imaginary path of, say, revolving path of the revolving electron or electron path of the electron. So, okay, it's a circular orbit and at a definite distance from the nucleus. The fourth point is, as you move away from the nucleus, the energy content of the orbit increases. Say farther the orbit, greater is the energy associated with that orbit. Therefore, as you go away from the nucleus, the energy of the orbit increases, or the orbit, that is the first orbit, which is nearest to the nucleus, it is having smaller energy compared to, or it is at lower energy compared to any other orbits higher than this. Okay, so the next point is electron while revolving in a particular orbit, it neither loses energy nor gains energy. Okay, the energy will not change, energy remains fixed as long as that electron revolving in that orbit. Okay, the electrons are revolving continuously in the orbit, and while moving they do not either absorb or lose the energy. Okay, energy remains the same. The next one, sixth point, suppose if the energy of the electron or energy is added to the electron or energy is removed, then that electron will change its position. That means, so if the atom is heated or it is supplied with certain amount of energy, then that electron absorbs the energy and it jumps to the higher energy level. So by absorbing the energy or by getting the energy, the electron shifts from one orbit to the another orbit. Suppose if the electron is present in the higher energy, and if it loses the energy, then it jumps to the lower energy level. So while coming to the lower energy level, it emits the radiation. Okay. So now that difference between any two orbit. Suppose say the electron is present in the second shell and it goes to the higher energy level by absorbing certain amount of energy. Then E2 minus E1. E2 is the higher energy of higher energy level, and E1 is energy of lower energy level, and it is given by the delta is equal to h nu. So h is a Planck's constant, nu is the frequency of absorbed radiation. Energy is nothing but radiation, isn't it? Similarly, suppose if the electron jumps from higher energy level to lower energy level, say from the fourth shell, if it jumps to the first shell, so E2 is fourth shell, energy of fourth shell, E1 is energy of first shell. The difference is equal to the energy emitted while coming back, while jumping to the lower energy level from higher, it emits the energy or it loses the energy in the form of radiation, and that is said to be a emitted radiation, and the frequency of that radiation is, say, it is nu. Therefore, E2 minus E1 either absorbed or emitted. Okay, that difference is always equal to h into frequency of that radiation, absorbed radiation or emitted radiation. So the last point is electron. Just you have seen when the electron shifts from one position to another position, when there is a change in energy. Okay, so now according to, say, the Bohr, the electron will occupy only those orbit. Electron will occupy only those orbit in which its angular momentum is exactly equal to n into h by 2 pi. Okay, so here m is the mass of electron, v is the velocity of electron, moving electron, and r is the radius of that orbit. So mvr, it is said to be a angular momentum. So the angular momentum of the electron, when it is equal to h by 2 pi, when it is equal to h by 2 pi, that means, say, the electron is occupied the orbit in which its angular momentum is equal to h by 2 pi. Okay, so or the electron may occupy any one of the higher energy level. Here h by 2 pi means n equal to 1, or it is nh by 2 pi. So that means the n may be first shell, second shell, third shell, or so on. So according to this postulates, it states that the electron occupies only those orbits in which its angular momentum is equal to the integral multiple of a whole number, that is of h by 2 pi, where n is a whole number. N is equal to 1 or 2 or 3. It is not a fraction. So this statement shows that, see, the angular momentum is quantized. Angular momentum is quantized. Okay. So now with this, we'll move on to the next one, that is interpretation about hydrogen emission spectrum of hydrogen atom. Interpretation about the emission spectrum of hydrogen atom. Okay, so now there is an experiment when the hydrogen gas at very low pressure, when it is heated by passing electric current, when it is heated, then in a, say, in a discharge tube, that is a glass tube, so in which hydrogen gas is taken and energy is passed, that means electricity is passed to heat that hydrogen gas at very low pressure. Okay, so when the current is passed, when they are supplied with certain amount of energy, the hydrogen atom absorbs the energy, and thereby the one electron, that is the only one electron which is present in the first shell, it absorbs energy and it jumps to any one of the higher energy level. And the jumping of electron from first orbit to any one of the higher orbit, that depends on the amount of energy absorbed by that electron. Okay, so now when they goes to higher energy level, there they are very unstable. So soon, that means soon after reaching the higher position, they returns back. That means they starts back journey. So while coming back, either they may jump to the directly for the first orbit from any of the higher orbit, or they may jump to the second orbit from any of the higher orbit, or third orbit from any of the higher orbit, or they may jump from to the fourth orbit from any of the higher orbit. Similarly, they may jump to fifth orbit from any of the higher orbit. Okay, so while coming back to the same orbit, they emit energy. They emit energy. So longer the wavelength, shorter the frequency, shorter the wavelength, longer the frequency. So that is also here it holds good. And when all the radiations, or when all the electrons from higher energy level, if they come to the first shell, and those, say, they radiate certain amount of energy. Okay, so by the jumping of higher orbit to the lower orbit, so energy will be emitted, and which is, say, studied by passing through the spectrophotometer, which is analyzed, and thereby, say, the spectrum is observed. Say for example, the spectrum which is said to be a line spectrum, and those lines are recorded on a, say, film, and those lines can be, okay, classified into, say, 5 series, and the first series is said to be a Lyman series, okay, Balmer series, Paschen series, Brackett series, and Fund series, okay. So like this, and these are the names of the scientists, those who have studied in detail, say, about the series which are observed in line spectrum of or emission spectrum of hydrogen atom, okay. So now there are totally, say, these lines are classified into 5 groups, okay, and they are named after the uh, discovered scientists, say Lyman, Balmer, Paschen, Brackett, and Fund series. And the Lyman series is obtained where N1, that is the smaller, that means lower energy level, and N1, it is the emission spectrum. That means the back journey is studied here, back journey of the electron from higher orbits to the any of the lower orbit, say it is studied. And those electrons which are coming from higher orbit to the first orbit, they are said to be Lyman series, and therefore where N1 is 1 and N2 may be, say, 2, 3, 4, and so on. And this energy radiations, they are falling in the region of UV region of electromagnetic spectrum. Similarly, Balmer series, where N1 is the second orbit and N2 is any of the higher orbit, and it is seen in visible region. Similarly, Paschen, where N1 is third shell and N2 is any of the higher shell, 4, 5, 6, and so on. And the series, that is the radiation or the lambda of that radiation or the frequency of that radiation, is falls in IR region, okay. And similarly, Brackett and Paschen series, and in those, say, N1 is fourth shell here and here it is fifth shell, and N2 is higher than this and N2 is higher than this, okay, and both of them are falling in IR region, okay. So now with this experiment we can determine or calculate the wavelength lambda, or say wave number of any line out of 3, any line. So you can calculate the wave number of that radiation. So by the expression or the equation, say, mu bar stands for wave number, or it is equal to 1 by lambda, and that is equal to r into 1 divided by n1 square minus 1 divided by n2 square, and that is in terms of per meter. So wave number, nu bar, lambda is wavelength. So now R is the Rydberg constant, and it is equal to 109.678 into 10 raised to 5 per meter. Okay, so like this, it is the explanation regarding Bohr's atomic model and also say interpretation about emission spectrum of hydrogen atom. Emission spectrum of hydrogen atom. Okay. So we can calculate the lambda of any of the, say, emitted radiation. Okay, we'll continue in the next class. Thank you.